what the students will be dealing with most of the time in exams are pressure versus volume graphs. Okay, so this here is a pressure versus volume graph. So let's say a gas is at a state over here at pressure P and volume Vi. Okay, so in moving, let's say the gas expands then at a constant pressure from here to here. Okay, so like we just deduced, the work done by the gas will be equal to the pressure multiplied by the final volume minus initial volume. Okay, if you think about it, that is simply the area under this graph over here. Okay, now what if firstly, this kind of a process where the pressure is constant is called an isobaric process. Okay, now we'll get back to isobaric processes in a while. Now usually what will happen is the gas will not stay at a constant pressure in moving from one state to another. Every point on this graph is a particular state, right? So in moving from here to, for example, this point here, okay, the gas might assume this kind of a trajectory. So now, how do we calculate the work done in such a situation? So what can be done now is that we divide this entire graph into small segments, small rectangular segments. Okay, and then we sum up all these rectangular areas. At each rectangular point, we have a particular Pi. Okay, and this multiplied by the small change in volume delta V, okay, and we sum up all those parts, okay, so till I we should get the work done. Okay, so again the work done by the gas is the summation of the individual pressure multiplied by change in volumes. Now this is the basic concept of integration, whereby in order to make this more accurate and include this lost area over here, what we do is we make these rectangles thinner. We make these rectangles infinitesimally thin so that the width here, delta V, is now dV. Okay, and the pressure multiplied by the infinitesimally thin rectangles, and instead of the summation sign, now we have an integration sign. This one will be the work done by the gas. And if you think about it, it's an addition of very thin rectangles, okay, which in the end will result in the complete area under this graph. Okay, the students are not expected to know integration, but they should know now that the work done by the gas is the area under the graph. Okay, so in coming from this state here till this state, the work done is the area under the graph. Okay, now we know from the equation of an ideal gas, PV equals nRT. Okay, so let's say at constant temperature, how does my pressure relate to volume? When the temperature is constant, this is constant, this is constant, this is constant. So all this is constant. Therefore, pressure is inversely proportional to volume. Okay, now that would mean on a pressure volume graph that would relate to a curve of this sort. Along this curve, the temperature is constant. Okay, let's say T1. Let's say I had a higher temperature T2. I know that the curve would be here. Okay, this here is T2, and another temperature T3, the curve would be here. Okay, where T1 is less than T2 and is less than T3. These curves are called isotherms. Okay, any process along this curve, okay, for example, if I come from here to here, okay, during this process my temperature is constant. Okay, temperature is constant which means from our previous discussion, it means that the change in internal energy is 0. Okay, therefore my work done, the heat added minus work done is 0. Okay, therefore the heat added is equal to the work done by the gas. So whatever work is done by the gas in expanding, that's the amount of heat that is added. Okay, therefore isothermic processes are slow processes generally, whether it's an expansion or a contraction, because you need to supply heat at the same rate as which the gas is doing work. Okay, so therefore these are slow processes. Now, anytime you're moving from a higher isotherm to a lower isotherm, it just means that the temperature is decreasing, and vice versa. So for example, in the previous process, we had an isobaric process which went from a lower isotherm to a higher isotherm, which means that the temperature increased, which means delta U was positive. Okay, and we also had work done by the gas. Okay, so we also know that W is also positive. Okay, so the internal energy is positive and also the work done is positive, and of course heat had to be added in order to increase the internal energy and the work done. Okay, another kind of process would be going down from here to here. Okay, so at this point the volume is constant but the pressure has reduced. Okay, so since there is no change in volume, the work done is 0. So the change in internal energy is simply the heat added or supplied. So if you take away heat, in this case of course heat is being taken away and therefore the internal energy is dropping. Okay, this kind of a process is called isovolumetric or isochoric. So those are the 3 kinds of processes, and the last kind, which is also quite important, okay, so I have one isotherm here and another isotherm here. So let's say a gas here at this state is expanded suddenly. Okay, so the sudden expansion means that there is very little or no time for a heat exchange. So 0 heat exchange, and when there is 0 heat exchange, that means there is no heat added, and therefore the change in internal energy is equal to the negative of the work done. So if there is work done in an expansion, my internal energy is going to drop, and therefore my temperature is going to drop. So the temperature dropped and the internal energy dropped. Work was done by the gas and the heat added was 0. This kind of a process is a fast process and it's called an adiabatic process. Okay, this kind of a line is called an adiabat. Okay, and an adiabatic compression would be the opposite. Adiabatic compression would be going from a lower isotherm to a higher isotherm. Now, processes within the cars, engines are usually more or less adiabatic because the piston moves so fast that there is very little time for heat exchange. So most of the processes within the car engines in the pistons are adiabatic processes. Okay, so that is the 4 kinds of processes. Right, so if we had a cycle of processes, for example, if a gas went from this point to here, then it went from here to here, then it went here, okay, and then back to this state. So in the exams there will usually be questions like of these sort. So for example, what is the total work done by the gas in this entire cycle from A to B to C to D to A? Okay, so in going from A to B, then you must recognize that the work done is the area under the graph. this is work done by the gas because it's expanding. Coming from B to C, there is no work done by the gas as there is no change in volume. From C to D, there is a compression, so this much work is done on the gas. Okay? And from D to A, again there is no work done as the volume is constant. So the net work done in moving from A to B to C to D to A should be the area enclosed within this structure over here. So this should be the work done. Okay, so this is the work done by the gas in one complete cycle. Sometimes in exam situations, it's important to note that they might just ask the work done by the gas in one step, even though they've given the complete cycle. So the students need to be a little wary of that. Now, 10.2.6. So that's taking care of the processes. Now we move on to engines, heat engines. So as you can see, this portion is actually pretty lengthy, and the students need to be aware of the concepts, the basic concepts over here, because most of the questions will be from this section. Okay, so 10.2.5 and 10.2.6 is about heat engines and heat pumps. So a heat engine is simply a machine, okay, or a device that converts thermal energy to work. So you have an engine, okay, and there is some useful work done. It draws energy from a hot reservoir, okay. Let's say this energy is QH, and it will give away energy QL to a cold reservoir. Okay. We will just realize this in a while, that it's impossible for an engine to completely convert all this energy to work. So some of the energy must be given off to a cold reservoir. Okay. From when we talk about engines, we will assume that the engine is an ideal engine for all purposes in ID. An ideal engine is one in which the change in internal energy of the medium is zero, which means that none of the heat which is carried by the medium increases the internal energy of the medium itself. Therefore, since the change in internal energy is zero, we have the heat supplied minus the work done equals zero. That means that the work done equals the heat taken away from the hot reservoir minus the heat supplied back to the cold reservoir. Okay, so this is a manifestation of the first law of thermodynamics in an engine.